All right, so this is a talk about statistical computing, and I guess in the theme of the workshop being big data. In the big data context, it's not meant to be a sort of tour de force of statistical computing. That I can't achieve that. More just some interesting vignettes, I think, on the space and some considerations. The first half of this talk will be fairly broad around that. If it seems a little bit nebulous, the first half, it's because it is a bit nebulous. But hopefully it sort of comes together. The second half will be about a new version of Libby that I've been working on. So for those who aren't familiar with Libby, this is a software package I've been working on for a little while. It's sort of to SMC what Stan is to HMC, or what JAGs and bugs are to Gibbs. And it has this sort of high-performance computing focus. So it runs on GPU and multi-core CPUs and distributed clusters and this sort of thing. So I sort of wanted to show you how this new version that I've been working on, and it should be available soon, addresses some of the considerations in the first part of the talk. So I wanted to start by thinking of statistics as an engineering discipline. That will horrify some people. I'm not putting it like this because it is engineering or because I necessarily believe it should be, but somehow by looking at it this way, I think there's some enlightening things that sort of fall out. So I want to ask the question, if I want to engineer a large statistical system, how do I approach this? So let's start with the sort of software side. A statistical system, we usually have a large software component. And these are the sort of 5 stages of what you call the waterfall model in software engineering. The waterfall model gets a lot of criticism. The question is where the arrows go between these stages. So the classic model, you have sort of arrows just going down the way. And basically, if you want to add a new arrow that goes up the way, you can write a book on that and sell it. This is a way you sort of develop new software engineering methodologies, okay? But essentially what you do here is requirements are that you write some analysis. This is the analysis stage, so you're listening to your users. What do I actually need to solve here? What do my clients need? Say, the design stage is to say, well, let's design a software architecture to address those requirements. The implementation is the coding part. Verification is your testing. Maintenance is your ongoing, maybe bug fixes and these sort of things. The ongoing deployment of the software. Now you can sort of think of, if we had statistical engineering, what are the sort of extra things you'd add in here? And of course there is a lot in statistics, because statistics has always been approached from a very rigorous viewpoint, right? So you have things like, prior elicitation. There is a bit of Bayesian bias here, you'll see. That's sort of the way I approach things. But prior elicitation, so talking to experts in the field and trying to write out some prior distributions. Experimental design is obviously a big one. Data acquisition, so how, what does it cost to get my data? What do I actually have available to me? And all these other sort of stages. Finally we sort of get to inference, which, those of us in computational stats spend a lot of time on. But model validation, model selection, decision making, decision theoretic frameworks and these sort of things. So there are these. I'm not suggesting this is the order or anything, or that these map one-to-one to this software engineering type approach. But these are all sort of quite rigorous considerations if you wanted to think about engineering a statistical system. So in terms of statistical computing, what I want to think about is all of this together. Where does statistical computing enter or support all of these processes? And there are some obvious ones like inference. We do a lot of inference in, say, R. We run some method, a Monte Carlo method or variational Bayes method or whatever we want to do inference. But of course, I think statistical computing really enters in most of these stages. If you think experimental design, for example, this is vastly more computationally expensive than inference, right? With inference, you have the benefit of having just a single data set, whereas experimental design, you now need to marginalize over all possible data sets that you might get, assuming that your model is the correct one, say. So this is a hugely computationally expensive thing that needs support from statistical computing. And there are other things too. If you think data visualization, what role does data visualization, say, play in prior elicitation or in the sort of requirements part from the software perspective? And of course, visualization is going to require some software to draw some pictures to inform these processes. So I wanted to add on top of that, in the big data context, what are the extra considerations? And you'll see the word that comes up there that I sort of think is synonymous with big data and what I think is perhaps the more interesting part of it, and that's complexity. Okay, and so we have these questions like, if we're going to deal with a problem where we require a vast amount of compute, we're going to have to deploy on a large computing system. And unfortunately, large computing systems are not just bigger laptops, okay? They're much more complex systems. You're talking distributed memory, you've got networks to deal with, you've got hardware like GPUs that are a bit more difficult to program than your more general purpose CPUs. So in terms of computing getting bigger, it doesn't just get bigger, it gets more complex, okay? I think the same can be said of data. In big data, we're not typically just interested in big N. Right? We're not even necessarily, I think, interested in big P. I mean, these are interesting questions, don't get me wrong. But it's not just that, right? It's not just that P gets bigger, say the number of predictors. It's also that we want to, say, combine multiple modalities of data. Okay, and so then you end up with, you've got sort of complex data, if you want to put it that way. That's the way I put it there as well. So you may have imaging data, you may have biometric data, genetic data, all these sort of different modalities that you sort of want to bring together. Which is more than just big P in the sense that it's also going to need a complex model to bring all that together. How do you link all these data sets? Well, you're going to need latent variables and things. You're going to need this sort of more complex model that brings them all together. And then once you've got a complex model, how do you solve it? Well, your method's going to get quite complex as well. And by that I mean, our methods these days are, we don't even necessarily just apply, say, MCMC to a problem. We're starting to kind of couple together different MCMC algorithms or different SMC algorithms. So in the SMC space, for example, which I'm more familiar with, we've gone from SMC to PMCMC, where we have SMC nested in MCMC. We've then gone to, say, SMC squared, where you have SMC within SMC, and MCMC moves on top of that. And then, of course, you want to Rao-Blackwellize when you can, so you've got some analytical solutions in there. So we're starting to really mix methods as well as models, I think, and so the methods have become more complex. So I guess I just wanted to, it's a bit subliminal here, but this complex is kind of the thing I'm interested in. And I think it's interesting from the statistical computing perspective because we want to say, well, what sort of software or what sort of languages allow us to deal with complexity, okay? So let me look at complexity first. The next few slides are just some vignettes, some interesting considerations, I think, in this space. So for models, for example, we want to be able to assemble complex models from simpler models. I think that's sort of what we want to do. By that I mean, to give you a bit of an analogy, in big data, we often talk about coming up with methods that are order n in the number of data points, okay? I'd argue that the way we actually implement our models is sort of order n squared in the number of variables, in this sort of sense, or n squared in the complexity. In this sort of sense, you're working on some project and you first of all you think, let's start with a simple model, okay, and some data. And we implement that. And we tend to, unfortunately, do this in a monolithic way where we've also chosen a method and a model and we've programmed it all in one massive R script, okay, that's going to do everything together. And now we say, okay, we've got some nice results there. Now we've got some new data, or maybe some part of the model doesn't fit so well. There's some new process we want to add. And so we add in a bit more model complexity, so some new component. And then what we really tend to do is sort of copy and paste this massive R script, okay, and then hack in the new bit. Now we've got two R scripts, one for the simpler model, one for the more complex model. And in a sense, this is my analogy, this is sort of an n squared approach to implementation, right? If you sort of see what I mean, right? We're always sort of re-implementing what we already had, and we have a lot of redundancy as a result. So maybe we want languages or platforms where we can reuse components more readily, sort of assemble these complex models from simpler models. Now that's what we do in object-oriented programming. So there are lessons to be learnt there. The big sort of thing with object-oriented programming is encapsulating complexity. Inheritance and polymorphism are also ways of dealing with complexity. And then I kind of want to say, well, I think there's probably been less thought put into this space, but as I said, I think the same maybe applies to methods. We want to assemble complex methods from simpler methods. And things like functional programming provide some nice ways of maybe dealing with that, of things like lambda calculus and these sort of things that let you assemble functions, if you like, in the same way that you might assemble objects in an object-oriented sense. Parallelism, I don't think there's much to say about. I think parallelism is obviously a consideration. You know, when we're dealing with complex models and complex methods, we're going to have to run on some parallel system. I think most people here actually appreciate that this is the case, so I don't want to dwell on it. All I wanted to say is that I think the particular type of parallelism we should be more interested in is data parallelism. Okay, there's these sort of two types. Data parallelism is essentially, I have lots of data items and I'm going to apply the same operation to them. Okay? Task parallelism is I've got multiple tasks to perform and they can be performed in parallel. So I'm doing completely different things. But almost everything I think we do in stats and even in scientific computing tends to fall into data parallelism. In fact, when we use task parallelism, like multi-threaded or multi-process distributed computing, we're often just using task parallelism to implement data parallelism. So a good example there is MapReduce. Okay, we're using a task parallel architecture, distributed memory architecture, but we're using it for data parallelism. We're distributing our data across, with this map operation across multiple processes. All right, so then there's a few other considerations too. What should our languages look like? Like, what does a good programming language look like? This is kind of a manifesto, or it's almost a poem actually, written by Tim Peters, who's one of the Python gurus. I think it's it kind of just captures some of the design principles behind Python, so you can kind of quickly skim read that if you like. The emphasis is mine. I've underlined a few things that I think are particularly important or that resonate with me. But you know, Python's actually a nice language because I think if the biggest complaint people have about your language is its white space, like that the negative space around your language is problematic, that's a pretty good language design, I think, if they're having to criticize you. Almost the criticism is what is not the language. Okay, and so, but there's a few things here that no one's going to complain about. I think this is like explicit is better than implicit is quite interesting. You don't want I interpret this to mean you don't want your language to be too clever. If you tell it to do something, you want to explicitly be telling it what to do. You don't want to be trying to interpret what you meant. Okay, so everything you say because if things are explicit, it's less error prone. Okay, these sort of things. This too, there should be one and preferably only one obvious way to do it. That's the complete opposite of Perl. Perl, for example, the language, it's always been there's more than one way to do it. But somehow when there's only one way to do it, it's a bit easier to communicate with other people, say, in the language. You both would do it the same way. So you don't get into these strange idioms and things. So these are just in terms of, I guess I've been thinking about language design as I've been working on this new version of Libby, and there's some interesting considerations in there. This is a little bit deeper. It's come up more recently, I think. How do we actually specify models? We have ways like graphical languages, graphical models and things for specifying models. And you can specify a model, say, by writing out its PDFs, or you can specify it, you can just sort of write a program that produces samples from it, okay? And I do wonder whether there's something actually quite deep going on here. There's been some work in this space. This is Breto and Ionides and others in the SMC space mainly have done this plug-and-play model idea. They're not the only ones who've worked on it, but the general idea there is that you've got a model whose prior distribution you can simulate from, but you can't evaluate that distribution point-wise. So say you've got a state space model where if I write down this density, so P of xt given xt minus 1, okay, if you give me an xt minus 1, I can simulate an xt, but if you give me an xt and an xt minus 1, I cannot evaluate that function point-wise, okay? These come up a lot in state space models because you have a lot of nonlinear processes. So a classic is like a nonlinear diffusion process, say, from xt minus 1 to xt. Okay, that's a classic model. So these are sort of this idea that there are some models where I can easily write them down as how do I simulate from them, but I can't write down their PDFs. Another term for those are black box models. And this is actually what a lot of the probabilistic programming languages are doing. I'll touch a bit more on that. You're writing a program that simulates from a distribution, basically. Approximate Bayesian computation is then very interesting because that's the same sort of idea but applied to the likelihood function. So I can simulate data, but I can't evaluate the likelihood function point-wise, okay? So again, there are some likelihood functions that I may want to describe in terms of simulation. There was this interesting paper that came out too on arXiv recently. I think it's going to appear in the American Statistician, that actually argues too that a simulation-based approach to teaching statistics can help people understand statistical concepts better as well. So that's an interesting, I found it, I'm not necessarily advocating that, but it was an interesting paper, more of an editorial type paper actually, about how simulation may assist people's thinking, even in understanding a p-value, for example. All right, so let me, I don't actually have heaps of time because we're running a bit behind, I guess, but let me talk a little bit about this new version of Libby and how I'm trying to incorporate some of that. So the first version of Libby, as I said, is kind of like Stan or JAGS or bugs, but for SMC. And it's always had this HPC focus, which I guess is what has distinguished it from other similar packages. So this new version of Libby, attempting to make it a more general purpose data parallel probabilistic programming language. So it preserved the HPC aspects of the first version while bringing in some of these things I've been talking about and some of the innovations in the probabilistic programming space. If you go to libby.org, there'll be some more on this new version soon. So where does it sort of fit in the scheme of things? We have, of course, a bunch of general purpose languages, and these, if you want to do statistical computing in these, there are various libraries available for them. Okay, we understand that. For statistical and scientific computing, we have some more specialized languages. Symbolic manipulation, if you're doing symbolic differentiation and stuff, there's software that supports that. This is my division here will be a little bit controversial to some people. There are these, what I'd call model specification languages, like bugs, JAGS, Stan, BIPs, and the current version of Libby, where you write out there's some language for specifying your model, and then you've got some software that reads in that specification and does inference on it. And then there's the probabilistic programming languages, which I think are trying to do something a little bit more, which is to integrate inference into the language. At least that's how I'd like to think about it. A bit like Prolog, if you've used Prolog before, does logic-based inference, right, and deduction. And you can do, automatic theorem proving and this sort of stuff in the language. Is that maybe that's where we're trying to go with probabilistic programming languages. I'm aware that a lot of people consider these probabilistic programming languages, especially Stan, because it has a more simulation-based model specification rather than a declarative model specification. I did talk about complex methods as well, and there's this package Nimble. I haven't played with it, but it's for sort of assembling Monte Carlo methods from components as well. So that's quite interesting. All I really wanted to say here, I would classify the current version of Libby here. This new version, I'm trying to move it more towards a language that you can do inference in. So let me just show you some simple examples of how this new language is working. So what I can do with Libby, I can declare a program. It's something I can run from the command line. Here, this is just a simple program that simulates some Gaussian variables. There's nothing too exciting happening here. I have these are command line arguments, so I'll be able to call it like this on the command line, or perhaps in future from R or MATLAB. Create a random number generator, seed the random number generator, declare a real variable, an integer variable, and I just loop over simulating. This is the more interesting line here. Okay, I simulate from a Gaussian distribution with the given mean and standard deviation, and I print it out. Okay, if I run that, it's just going to print out 5 Gaussian random variables. Okay, really simple program. This is sort of syntax becomes interesting. So the question is, what can we do with this? You can, in this new version of Libby, you can pass expressions to functions. Okay, in a very rich sort of way. So I can do some cooler things too, okay? Let me move on. Similar program again, but this time I'm simulating using the simulate posterior normal variance, where I have some prior distribution over the mean. Okay, so sorry, I'm simulating the mean, in fact. So I can this line, the program is much the same except now for this line, okay? So I now have, I've got some observation y, okay, coming from this distribution, and I have a prior Gaussian distribution over x, so the mean of that distribution, okay? And now this in Libby, it understands what this means, okay? It knows how to apply the conjugacy to simulate from the correct posterior distribution. Okay, how does it know to do that? It's kind of not any magic. There's this function, simulate, that's overloaded for that form of expression, and it evaluates the correct mean and standard deviation using conjugacy. So we could well, I haven't done it as yet, it's ongoing work. You can program in all the standard conjugacy type arguments. But what I like about this is just the idea that, in that Zen of Python, that explicit is better than implicit. I think writing this, rather than writing out the code that evaluates that, it's much clearer what I'm doing. Okay, it's much clearer what my model is doing. And I'm not losing any performance because I'm compiling down to C++ anyway. Here's another little idea. What if I want to just simulate from any distribution but truncating it within some interval, okay? So I introduce this indicator function. The indicator function has no body because I'm just going to use it in sort of mathematical sort of expressions. And now I can say here, I can declare this simulate function in a way that says, if you're going to say x is distributed according to, this just means any expression, and the colon with no type afterwards means of any type. Okay, so you just think of this as any expression. And you want to multiply it by this indicator function, then what I'm going to do is this. This is what it's going to mean. This is rejection sampling, okay? I'll simulate an x from that expression, and while that x is not in the bound that I was given, I'll simulate another one. Okay, so really just a simple rejection sampler. For any, given we know nothing about that expression, this is a sensible thing to do. Clearly, if the truncation is very tight, the rejection rate will be very high, and this isn't necessarily going to work quite well. But as a base default implementation, that seems sensible. But now I could say, well, I can also overload this for the special case where it's a Gaussian distribution. Okay, and we have methods that are more efficient for simulating from truncated Gaussian distributions. And so I could overload in there. I haven't done so. I've just shortened the slide. But there's an overload in there for that particular case. So how is that working? There's this idea in Libby that every code fragment, there's a partial order over all possible code fragments. Okay, and it looks something like, just as an example, the reason that when I sample from a Gaussian, if I go back, the reason this might be picked over this is if it's more specific, if it's a more specific match to the function call that the user has made. So the point with this is essentially there's a partial order over all code fragments. The partial order is defined according to the parse tree. Okay, and what happens here is that this is a more general node than this. It's allowed to capture this. So this is considered a more specific code fragment than this. Or if you like, this is less than this in the partial order. Okay, and so when you call a function, it always chooses the most specific overload that matches. Okay, it is a partial order, so there can be ambiguities that will result in a compile error. Okay, great. So what I wanted to point out is that this is sort of a way of handling some method complexity. Okay, it's still the same simulate function, but I can overload this simulate function for all sorts of different models. Here it's just a Gaussian versus a truncated Gaussian or something like that. It could be more elaborate. It could be a state-space model. It could be some Bayesian logistic regression model or something like that. It's still always a simulate function, as opposed to simulate underscore SSM, simulate underscore Bayesian logistic model or something like that. Okay, so this is just one of the ways that method complexity is being handled. I haven't done anything about models at this stage. So one of the things you want to do is you want to decouple methods and models. And as I said, the way of handling model complexity, we should draw some inspiration from object-oriented programming. So what I've done here, this is really simple again, but this is a generic model with a prior distribution. Okay, where the prior distribution isn't defined. Okay, this is going to be, for those familiar with it, an abstract function. And then I can inherit from this and define my specific model, which is just going to have two parameters, mu and sigma. And I'm going to put a prior distribution over those parameters that looks like this, okay? The point of this is that for most users, I would hope that all they have to do is write this sort of stuff. So they use this new version of Libby like you use Stan or Bugs, or the current version of Libby, okay? Then the point is here, this simulate prior function is inherited as well. So I can actually call simulate prior on this, and it will simulate what I've written there. Okay. So here's just an example of how this might look like. So again, it's just a standalone program. But here I declare an array of those models that I've just declared, and then I just loop over that array and I call simulate prior. Okay, and then I'm going to output the results to a netcdf file. I'll come back to that. The point here is that the complexity of that model, it's not very complex in this case, but it could be a complex model, is encapsulated. Okay, there's no this method, if you like, for simulating is isolated from the interior complexity of that model. So this is just the encapsulation thing in object-oriented programming. A couple of things. I've only got a few minutes. Let me just explain a few things. I've only got a few more slides. What does this array look like? I also said it's a data parallel language, okay? And so what I need is an efficient memory layout. Usually in C or C++, or anything, in fact, that model I've declared is going to look like this at the end of the day, a structure with two variables, mu and sigma. And when I declare an array, it's going to be what's called an array of those structures. What that means is that the memory order is mu1, sigma 1, mu2, sigma 2, mu3, sigma 3, etc. It's not very good for parallelization, okay? I want to have instead all of my mu's in one string, like mu1, mu2, mu3, mu4, and then sigma 1, sigma 2, sigma 3, sigma 4. Okay, it's a more efficient memory layout for GPU and vector operations. And in fact, I've got to be quick here, but Libby is using this sort of syntax, which is nice for dealing with model complexity. It's the object-oriented syntax. It's using this memory layout under the hood. It's using an efficient memory layout for data parallelism under the hood. Okay, so this is a way of handling model complexity without compromising performance. Okay, that's what it's trying to do there. And just to say too, there's some efficient I/O routines. So netcdf files are a high-performance file format. And again, there's some encapsulation here. I can just output my model or even an array of models straight to a netcdf file without knowing the details of that model. And in fact, the details of the model are preserved in the file. Okay, so this is just the file that I've written out. There's this nc dump program. You can see its contents. Okay, so I'll actually wrap up there. So just to summarize, I guess I've started there with some considerations, not a comprehensive consideration of statistical computing in the big data space, but some things like data parallelism, complexity of models and methods and so forth. And just some of the ways this new version of Libby is trying to holistically incorporate these things into a language for probabilistic programming. Okay, thank you.
We have time for a couple of questions, if anybody is wanting to contribute. I know that some people suffer from coffee deprivation at this stage, like me. But
I'm sorry, Jim, I have another question. First, what is there something specific you could point to that makes the new Libby a probabilistic programming language as opposed to a declarative?
Yeah, so this is I think I'm not even sure we know what the definition of probabilistic programming language is yet. Have we sort of settled on it? It's kind of it's still a bit nebulous to me as to what it is. I mean, I think things like that. Well, I could go back, but things like that conjugacy. I think this is the sort of I can imagine this becoming a bit more sophisticated. Where you can couple together a much more complex prior, like a state space model, with a much more complex likelihood, and ask it to do inference and have method overloads that are able to handle that, for example. So somehow I feel like with this, you may be able to write, I guess because the language is not just about models, but also about methods, you're putting them both into the one language, that maybe you can even... It feels a bit more like I think the thing we should be aiming for is something like Prolog was for logical programming, where you can kind of, even if say it was interactive, this is compiled, but say it was interactive, that you could actually sort of write out these models and then say, please tell me, you write out your joint distribution, and then just say what is the posterior given this data set, and this sort of all happens interactively, say. But as I said, I'm not sure we still. What's the definition of a probabilistic programming language? I'm not sure we've really pinned it down yet. like what we're trying to achieve. So.
Okay.